Hey everyone, and welcome back to Hafee Sleep. Whether you're tuning in from a bustling city where the lights are just coming on, or you're in a quiet town where everyone else is already dreaming, whether it's the middle of the day for you and you need a cosmic escape, or it's deep into the night and your mind is craving a truly big thought, I am so glad you're here. Before we drift off into the cosmos tonight, if you're on a journey of curiosity with us, make sure you've subscribed to the channel and hit that like button. It truly helps us grow this little community of starry-eyed dreamers, and lets me know you enjoy these deep dives into the universe's greatest mysteries. And while you're there, I'd love to know, where in the world are you watching from, and what time is it for you? Drop a comment down below, and let's see just how far and wide our Hafee Sleep family stretches. It's always amazing to connect with you all. Now get comfortable. Close your eyes if you like, and let your mind expand. Because tonight, we're unraveling one of the most fascinating detective stories in all of science. It's a tale involving the greatest genius of the 20th century, a discovery he called his biggest blunder, and how that very mistake, decades later, led us to the edge of a mystery so profound, it defines the fate of our entire universe. We're talking about the invisible force that makes up most of reality, the enigmatic push known as dark energy. And it all starts with a fudge factor in an equation, dreamed up by a man named Albert Einstein. Imagine, if you will, the universe as a vast, dark, and silent ocean. An ocean so unimaginably enormous that every star, every galaxy, every flicker of light we can see from our tiny little world is nothing more than a single, solitary glow from a lantern on a distant ship. For a long, long time, we sailors on spaceship Earth looked out at this dark ocean and thought we understood its currents. We believed that the grand movement of these galactic ships was governed by a simple, predictable rule: the gravitational pull of all the matter within the universe. After the Big Bang, the initial explosive rush was slowing down, and everything, all those beautiful islands of stars, were gently, gracefully, drifting apart from one another, coasting on the momentum of that primeval explosion, but gradually slowing down, like a ball thrown high into the air that pauses for a moment at its apex before succumbing to gravity's pull and falling back to Earth. It was a majestic, serene picture of a cosmos expanding, yes, but also slowly winding down. It was a universe that made sense. But then, in the last years of the 20th century, a handful of astronomers decided to measure this slowing down, to put a number on the deceleration of the cosmos. They pointed their telescopes at the deepest, darkest stretches of space, not to look for new islands, but to carefully clock the speed of the ones we already knew. They were trying to catch the universe in the act of breaking, and what they found, to their absolute and profound astonishment, was that the universe wasn't slowing down at all. The ball wasn't falling back. It wasn't even hovering at the apex. It was shooting away from our hand faster and faster, as if it had been filled with some mysterious, invisible helium. The universe, against all logic and expectation, was accelerating. The brakes were off. The pedal was pressed to the metal. And this discovery, this shocking paradigm-shattering revelation, pointed to one inescapable, bewildering conclusion. Something was out there in the dark ocean, something we couldn't see, a hidden current pushing every single galaxy apart, with ever-increasing force. They called it dark energy. And the story of how we found it, how we're sure it's there, is one of the most thrilling detective stories in all of human history. It's a tale that begins not with a complex equation, but with a mistake. a beautiful, brilliant mistake made by the greatest scientist of the 20th century. Our story really starts with Albert Einstein. In 1917, he was applying his magnificent new theory of gravity, the general theory of relativity, to the entire universe. So, let's settle in and really unpack this moment, this incredible crossroads in the history of science, where the greatest mind of his era, perhaps of any era, found himself at a loss. We're talking about Albert Einstein in 1917. The world is still reeling from the horrors of the First World War, but in the quiet halls of theoretical physics, a revolution is already complete. Einstein's general theory of relativity is barely 2 years old, and it's already shaken the very foundations of how we understand reality. It's a theory of breathtaking beauty and profound strangeness. Before Einstein, we thought of gravity the way Sir Isaac Newton told us to, as a mysterious, invisible force that reached out across space, pulling the apple to the ground and holding the moon in its orbit around the Earth. It worked. It was brilliant. But it never explained how that force worked. It just did. Einstein's genius was to offer an explanation, and it was a doozy. He proposed that space and time aren't just a static, empty stage upon which the drama of the universe plays out. Instead, he said that space and time are woven together into a single flexible fabric called space-time. And this fabric isn't rigid. It's soft, pliable, dynamic. It can bend, it can warp, it can curve. Now, what causes it to bend? Matter and energy. Anything that has mass, a planet, a star, a cup of coffee, warps the space-time around it. Imagine placing a heavy bowling ball in the center of a taut, stretchy trampoline. The trampoline's surface dips and curves under the weight. Now, roll a marble across that trampoline. It won't roll in a straight line. It will curve inward, following the dip created by the bowling ball. The marble is, in a sense, attracted to the bowling ball, but there's no mysterious force pulling it. The marble is simply following the path, the groove, the geometry of the curved surface. That's gravity in a nutshell. The bowling ball, a star, tells the trampoline, space-time, how to curve, and the curved trampoline tells the marble, a planet, how to move. Mass tells space-time how to curve, and curved space-time tells mass how to move. It's a sublime, elegant dance between the contents of the universe and the stage itself. And Einstein's theory wasn't just a pretty idea. It made a concrete prediction. It said that if space-time is curved by mass, then even something massless, like a beam of light, should have its path bent when it travels through warped space-time. It should follow the curve. This meant that light from a distant star, passing very close to the edge of our massive sun, should be deflected from a straight path by a tiny but measurable amount. In 1919, just a couple of years after our 1917 story, an expedition led by Sir Arthur Eddington traveled to Africa to observe a total solar eclipse. During the eclipse, the moon blocks the blinding light of the sun, allowing astronomers to see the stars right next to the sun's blacked-out disk. They took pictures and measured the positions of those stars. And lo and behold, the stars appeared to be slightly out of place, exactly as Einstein's theory had predicted. The sun's gravity had bent the starlight, acting like a lens. Overnight, Einstein became a global superstar, the man who had rewritten the laws of the universe. His face was on the cover of magazines everywhere. He was the genius's genius. So, flush with this monumental success, Einstein did what any brilliant theorist would do. He turned his new tool, this powerful set of equations called general relativity, onto the biggest problem he could find. He aimed it at the entire universe. This was an act of incredible audacity. Imagine you've just invented the most sophisticated microscope ever conceived, and the first thing you do is point it at the entire sky. You're not just looking at one object, you're trying to understand the entire system, the whole grand kit and caboodle, all at once. He wanted to see what his equations said about the cosmos's overall behavior, its shape, its structure, its destiny. But here he ran into a wall built not of mathematics, but of assumption. You see, in 1917, the prevailing wisdom, the common sense view shared by every astronomer, including Einstein, was that the universe was static. It was eternal. It was unchanging. It was just there. The stars twinkled in their fixed positions. The Milky Way was thought to be the entirety of the universe, a single vast island of stars floating in an infinite, empty, black void. The universe had no beginning, and it would have no end. It was a permanent, frozen sculpture. This idea was so deeply ingrained that it was considered an obvious, unquestionable fact. So, Einstein began to work with his equations, trying to model this static, unchanging cosmos, and the equations rebelled. They refused to cooperate. No matter how he massaged them, they would not yield a stable, static solution. The problem was gravity. His own beautiful theory of gravity was the problem. Gravity, as he had so brilliantly described, is an attractive force. It pulls things together. It doesn't push things apart. So, if you imagine the universe is filled with stars and galaxies all exerting a gravitational pull on each other, what should happen? Everything should start to fall inward. All that matter, pulled by mutual gravity, should cause the entire universe to begin collapsing in on itself. It would be a cosmic scale version of a building imploding. All the matter would rush towards a central point, culminating in a big crunch, a fiery, catastrophic end to everything. The only other possibility his equations allowed for was if the universe was already moving, expanding outward from some initial point with tremendous energy. In that case, gravity would be acting like a brake, slowing that expansion down, but it wouldn't necessarily collapse immediately. It could keep expanding for a long, long time, just getting slower and slower. But a universe that was just sitting there, perfectly still, not moving, not expanding, not contracting. The mathematics said it was impossible. It was like trying to balance a pencil perfectly on its point. The slightest perturbation, and it would fall over. A static universe was inherently unstable in the world of general relativity. This was a profound crisis for Einstein. On one hand, he had his magnificent equations, which had already been proven correct. They were the most accurate description of gravity ever devised. On the other hand, he had the unanimous opinion of every astronomer in the world, backed by all available observational evidence, which said the universe was static. What was he to do? Believe the math or believe the scientists? It was a classic conflict between theory and observation. Einstein, perhaps surprisingly, chose to trust the observations. He was so convinced that the universe had to be static that he decided the problem must lie with his equations, not with reality. He believed his math was incomplete. So he did something that theorists sometimes have to do. He added a term. He introduced a little fudge factor, a mathematical fix, to make the equations behave. He called this term the cosmological constant. In his equations, it's represented by the Greek letter lambda, L. Now, what was this thing? It wasn't an additional source of matter. It wasn't a particle or a gas. It was something far more subtle and strange. It was a property of space itself. Empty space, according to this new idea, wasn't just nothingness. It had an intrinsic energy, a built-in tension. And this energy had a repulsive quality. It was a kind of anti-gravity. Think of it like this. Imagine the force of gravity between all the galaxies is like a group of people all holding hands and pulling inward, trying to form a tighter and tighter circle, collapsing the party. Now imagine that the very space between those people is made of a special, springy material. The more you stretch that material, the farther apart the people are pulled, the more it pushes back. It resists the stretching. But in this case, Einstein's cosmological constant was a very special kind of spring. It made empty space itself want to push outward, to expand. It was a repulsive force woven into the vacuum. His idea was that on the very largest scales, this repulsive push of the cosmological constant could exactly balance the attractive pull of gravity. If he could just tune the value of lambda just right, the two forces would cancel each other out perfectly. The inward tug of gravity and the outward push of lambda would be in a perfect, delicate, and eternal standoff. The universe would be like a ball, perfectly balanced on the very top of a hill, motionless, never rolling down either side. It could be static. It could be unchanging. It could be the universe everyone believed in. In his mind, this wasn't a cheat. It was a necessary modification to make the theory fit the observed facts. It was a fix to preserve the static universe model. He later would come to regret this deeply, famously calling it the biggest blunder of his career. But at the time, it seemed like a logical, even clever solution. He had, in a way, prioritized the scientific consensus of his day over the pure, unadulterated prediction of his own theory. He had chosen the map over the territory. Little did he know that within a decade, the territory would be revealed to be far stranger and more dynamic than anyone had ever dreamed, and that his blunder would be resurrected decades later to explain a mystery even he couldn't have imagined. He had the key to the expanding universe in his hand, and he threw it away to maintain the status quo. It's a powerful reminder that even geniuses are products of their time, and that sometimes the universe is waiting to surprise us all. Then, just over a decade later, a young American astronomer named Edwin Hubble, working with the powerful new Hooker telescope on Mount Wilson, made a discovery that shattered the static universe forever. So, let's really set the stage for this monumental moment in human history. It's the 1920s. The world is recovering from a global war. Jazz music is filling the airwaves, and a newfound sense of modernity is taking hold. But up on a mountaintop in California, far from the hustle and bustle, a quiet revolution is brewing. One that will forever change our understanding of our place in the cosmos. To appreciate just how earth-shattering Edwin Hubble's discovery was, we have to put ourselves in the mindset of people back then. For centuries, the prevailing view of the universe was profoundly local. We knew about the planets in our solar system. We knew about the sun. And we knew about the countless stars that formed a great milky band across the night sky, our Milky Way galaxy. This was it. This was the universe. Everything astronomers could see through their telescopes was thought to be contained within this single, colossal island of stars. It was a comfortable, if grand, picture. We were at the center of everything. But there were these puzzling little smudges in the sky, these fuzzy, spiral-shaped patches of light that astronomers called spiral nebulae. The word nebula just means cloud. The big question, the subject of what was known as the Great Debate among astronomers was, What are these clouds? Are they relatively small, nearby clouds of gas and dust, perhaps other solar systems forming within our own Milky Way? Or are they something else entirely? Could they be vast, distant collections of stars, island universes, separate from our own galaxy? It was a debate between a small, cozy universe and a potentially immeasurably larger one. There was no way to know for sure because nobody could accurately measure their distances. It's like looking at a streetlight in a thick fog. You can see it's there, but you can't tell if it's a small light close to you or a massive, brilliant light very far away. Enter Edwin Hubble. He was a character straight out of central casting for a Hollywood academic. Tall, athletic, with a commanding presence and a pipe often clenched between his teeth. He was a former Rhodes Scholar, a one-time lawyer, and even a decorated soldier from World War I. He was ambitious, brilliant, and he had an almost theatrical flair about him. And most importantly, he had access to the most powerful telescope in the world at the time, the magnificent 100-inch Hooker telescope at the Mount Wilson Observatory. This telescope was a giant of its age, a colossal eye on the sky that could see deeper and with more clarity than any instrument before it. It was the key that would unlock the cosmos. Hubble's first task was to solve the distance problem. How do you measure the distance to something impossibly far away? You need a standard candle. This is an astronomer's term for an object whose true intrinsic brightness you know. Think of it like this. If you know a light bulb is a 100-watt bulb and you see it looking very dim, you know it must be very far away. If you see a 100-watt bulb looking very bright, you know it's close. The trick is finding a light bulb in space where you know its wattage. Hubble found his standard candle in a special kind of star called a Cepheid variable. Now, Cepheid variables are fascinating. They are stars that pulsate, rhythmically growing brighter and dimmer over a period of days or weeks. The crucial discovery, made by the brilliant astronomer Henrietta Swan Leavitt a few years earlier, was that there is a direct relationship between how long it takes a Cepheid variable to complete one pulsation cycle, its period, and its true brightness. A Cepheid that pulses slowly is intrinsically very, very bright, a real powerhouse. A Cepheid that pulses quickly is intrinsically much dimmer. This was a universe-altering revelation. It meant that just by watching a Cepheid variable and timing its pulse, an astronomer could know its true wattage. Then, by measuring how dim it appeared from Earth, they could calculate exactly how far away it must be. It was a cosmic ruler. Hubble pointed the gigantic eye of the Hooker telescope at the most famous spiral nebula, the Andromeda Nebula. He took painstaking long-exposure photographic plates night after night, searching for these telltale blinking stars within its spiral arms. And after a long, careful search, he found them. He identified several Cepheid variables. He timed their pulses, which told him their true, colossal brightness. Then he measured how faint they appeared in his telescope. The math was undeniable. The distance was staggering. The Andromeda Nebula wasn't a nearby cloud. It was nearly 1 million light-years away. We now know it's 2.5 million light-years, far, far outside the confines of the Milky Way. It was an entire other galaxy, an island universe containing hundreds of billions of stars, a twin to our own Milky Way. In one breathtaking observation, Hubble had exploded the classical view of the universe. The cosmos wasn't just our backyard. It was a vast, sprawling metropolis of galaxies, each a colossal island of stars, separated by unimaginably vast gulfs of empty space. The scale of everything had just expanded by a factor of 1,000,000. We were not the center of the universe. We were residents of a single, ordinary suburb in a never-ending cosmic city. It was the ultimate lesson in humility. But Hubble wasn't finished. He had answered the what and the where. Now he turned to the how. How were these galaxies moving? To understand this, we need a quick lesson in the Doppler effect. You experience the Doppler effect every day. When an ambulance races towards you with its siren blaring, the sound waves are compressed, making the pitch sound higher. As it passes you and moves away, the sound waves are stretched out, making the pitch sound lower. Wee-oo. Light behaves in exactly the same way. If a source of light is moving towards you, the light waves are compressed, shifting the light towards the blue end of the spectrum. This is called a blue shift. If a source of light is moving away from you, the light waves are stretched, shifting the light towards the red end of the spectrum. This is called a red shift. By splitting the light from a galaxy into a spectrum, a rainbow, and looking for the telltale fingerprints of specific elements, astronomers could see how much those fingerprints were shifted towards the red or the blue, and calculate the galaxy's speed towards or away from us. Other astronomers, like Vesto Slipher, had already been collecting this data and found something peculiar. Most galaxies showed a redshift. They were moving away from us. Hubble, working with his meticulous assistant Milton Humason, took this velocity data and combined it with his new distance measurements. He plotted a simple graph. On the bottom, he put distance. On the side, he put velocity. If galaxies were just moving around randomly, the points on this graph would be a scattered mess. Some would be moving towards us, blue shifted. Some away, red shifted, with no pattern. But that's not what Hubble saw. The points lined up. They created a stunning, near-perfect straight line rising from the corner of the graph. This was mind-blowing. It meant there was a direct proportional relationship. The farther away a galaxy was, the faster it was receding from us. A galaxy twice as far away was moving twice as fast. A galaxy 10 times farther away was moving 10 times faster. This wasn't random motion. This was a coherent, organized pattern on a cosmic scale. The entire universe was expanding. The space between the galaxies was itself stretching. The best way to picture this is the famous inflating balloon analogy. Imagine a balloon with little dots on it. As you blow up the balloon, every single dot moves away from every other dot. If you are an ant sitting on one dot, you would see all the other dots moving away from you. The dot closest to you moves away a little bit. A dot on the far side of the balloon moves away a lot. And crucially, the farther away a dot is from you, the faster it appears to be moving away. This is exactly what Hubble discovered. It's not that galaxies are flying through space away from us. It's that the very fabric of space between us and them is expanding, carrying them along for the ride. We are not at the center of this expansion. From any other galaxy, the view would be exactly the same. Everyone sees everyone else moving away. The universe itself is getting bigger. This was the final definitive nail in the coffin for the static universe model. The cosmos was dynamic, evolving, and growing. And in a beautiful, almost poetic twist, this was the exact kind of universe that Einstein's original, unaltered equations of general relativity had predicted. He had the right answer in his hands a decade earlier and had thrown it away because he didn't believe it. The story goes that Einstein visited Hubble at Mount Wilson, looked through the great telescope, and conceded his error, famously calling the introduction of the cosmological constant the biggest blunder of his career. He had invented a fudge factor to make his equations match what everyone thought was true, when in reality, his pure math had been trying to tell him a deeper, more astonishing truth. The cosmological constant was scrubbed from the textbooks, dismissed as an unnecessary mistake. The universe was expanding, and that was that. It seemed like the story was over. But the universe, as it turns out, loves a good plot twist. The cosmological constant was just waiting in the wings, ready for a dramatic comeback many decades later. The goal now was to measure how that expansion was changing over time. Everything had gravity, and gravity pulls things together. So, even though the universe was expanding, that expansion must be slowing down, resisted by the collective gravitational tug of all the galaxies, gas, dust, and dark matter pulling on each other. The big question for cosmologists throughout the mid-20th century became, by how much? How fast is the expansion slowing? Will it slow to a stop? Will it eventually reverse and cause a big crunch? Or will it just keep expanding forever, thinning out into a cold, dark eternity? To answer this, astronomers needed to measure the expansion rate, the Hubble constant, with immense precision, and they needed to see how that rate changed over billions of years. To do that, they needed a special kind of cosmic yardstick. They needed a standard candle. As I have previously explained, a standard candle in astronomy is an object whose true intrinsic brightness we know. Imagine you're standing on a long, straight road at night, looking at streetlights. If every single streetlight is identical, the same wattage bulb, the same design, then you can tell how far away each one is just by how bright it appears. The dimmer it looks, the farther away it is. This is the inverse square law of light. Apparent brightness drops off with the square of the distance. If one light looks 4 times dimmer than another, it's twice as far away. Easy. The challenge in space is finding those identical streetlights. Most stars and galaxies come in all sorts of varieties and sizes. But astronomers found a fantastic one, a specific type of stellar explosion called a Type 1a supernova. A supernova is one of the most violent and energetic events in the universe. It's the catastrophic death of a star, so brilliant it can outshine an entire galaxy of billions of stars. A Type 1, a supernova, has a very specific origin story. It involves a binary star system, 2 stars orbiting each other. One is a white dwarf, the incredibly dense, Earth-sized core of a star like our Sun that has run out of fuel. The other star can be a giant star or another white dwarf. The white dwarf, with its immense gravity, starts siphoning material, mostly hydrogen, off its companion. This stolen gas piles up on the surface of the white dwarf. The white dwarf is made of a stuff called degenerate matter, which is supported against its own gravity not by heat from fusion, but by quantum mechanical effects. It's like a can of soda that's been shaken up. There's a tremendous pressure waiting to be released. As the white dwarf gains mass, its core gets hotter and denser. There is a very precise limit, called the Chandrasekhar limit, about 1.4 times the mass of our Sun, which this degenerate matter cannot exceed. Once the white dwarf reaches this critical mass, the pressure and temperature in its core become so extreme that it can no longer hold out. The carbon and oxygen that make up the white dwarf suddenly ignite in a runaway thermonuclear fusion reaction. In a fraction of a second, the entire white dwarf is torn apart in a titanic explosion. This is a Type 1a supernova. The key point is the physics, because every single one of these supernovae is triggered by a white dwarf hitting the exact same mass limit, the Chandrasekhar limit. The explosion is incredibly uniform. they all release almost exactly the same amount of energy. They are the perfect standard candles. They are our identical cosmic streetlights. By the 1990s, technology had advanced to the point where we could reliably find these supernovae in galaxies billions of light years away. Two major international teams formed, almost like competing sports teams, to hunt for these distant explosions and use them to measure the deceleration of the universe. They were the Hafee Supernova Search Team, led by Brian Schmidt, and the Supernova Cosmology Project, led by Saul Perlmutter. Their plan was meticulous. They would find these supernovae in extremely distant galaxies. Because light takes time to travel, looking at a galaxy a billion light years away is like looking a billion years into the past. They would measure the redshift of the supernova's host galaxy to tell how much the universe had stretched since the light left the explosion. The redshift is a direct measure of how fast the galaxy was moving away from us when the light was emitted. Then, they would measure the apparent brightness of the supernova. Since they knew its true brightness, being a standard candle, its apparent dimness would tell them its distance. By comparing the distance from brightness to the recession velocity, from redshift, for many supernovae at different distances, and therefore from different epochs in cosmic history, they could plot how the expansion rate of the universe had changed over billions of years. They expected to see that for more distant, older supernovae, the expansion rate was faster. The universe was slowing down. They were all set to measure the deceleration parameter. They were about to weigh the entire cosmos and determine its ultimate fate. So, let's really put ourselves in the shoes of these two teams of astronomers in the late 1990s. The stage is set for what they believe will be the crowning achievement of 20th century cosmology. They have the tools, the theory, and the targets. The goal is noble and clear: to measure the deceleration of the universe. For decades, the expanding universe had been settled science. Everyone knew the story. The Big Bang had set everything in motion, and ever since, the mutual gravitational attraction of all the matter in the cosmos, the galaxies, the gas, the mysterious dark matter, had been acting like a brake, steadily slowing the expansion down. The only questions left were, how much is it slowing? What is the ultimate fate of everything? Will the expansion eventually halt and reverse, leading to a fiery big crunch? Or will it just keep going forever, slowing to a crawl, destined for a cold, dark, and lonely end, a heat death where everything is so spread out that the universe effectively goes to sleep? These weren't just academic questions. They were about the ultimate destiny of all existence. And these two teams, the Hafee Supernova Search Team and the Supernova Cosmology Project, were going to answer them. They were like two groups of explorers racing to be the first to the North Pole. Only their pole was a number, the deceleration parameter, a value that would tell us how the universe's expansion has changed over time. Their tool, as we discussed, was the Type Ia supernova, the perfect standard candle. Their method was elegant. They would find these brilliant explosions in galaxies near and far. The light from a supernova in a nearby galaxy gives you a baseline. You see how bright it really is up close. Then, you find supernovae in extremely distant galaxies. Because light takes time to travel, looking at a supernova a billion light years away is like looking a billion years into the past. You are seeing the universe when it was younger. For each of these distant supernovae, you do two things. First, you measure its redshift. This tells you how much the universe has stretched since the light left the explosion. which directly gives you the expansion velocity of the universe at the time the supernova went off. Second, you measure how bright the supernova appears in your telescope. Because you know its true intrinsic brightness, it's a standard candle. Its apparent dimness tells you its distance. Now here's the key. In a universe whose expansion is steadily slowing down, there is a very specific relationship you expect to see between redshift, velocity, and distance, brightness. Think of it like this old, familiar story. Imagine a driver who slammed on the brakes a while ago and is now coasting, slowing down. If you know how fast the car is going right now, and you know how hard they hit the brakes, you can calculate how far they've traveled since they started braking. The astronomers thought the universe was this car. They knew its current speed from nearby supernovae. They thought they knew about the braking force, gravity. So, for a supernova from long ago, its redshift gives you the speed of the universe back then. Its brightness tells you how far away it is, which tells you how much the universe has expanded since then. They expected to see that for a given redshift, a given historical speed, the supernovae would be closer than they would be if the expansion had been constant. Why? Because if the universe was moving faster in the past, as it must have been if it's been slowing down, then it would have covered more distance in the early epochs than a steady speed universe would have. It would be like our braking car. If you see it going 60 mph now, but you know it was braking, you know it must have been going even faster, say 80 mph a minute ago. Therefore, in that minute, it would have covered more distance than if it had been going a steady 60 mph for that whole minute. So, if you looked back in time and saw it when it was going 80 mph, you'd expect it to be farther away from its starting point than a car that had been doing a constant 60 mph. Translating this back to the universe, if the expansion is decelerating, the ancient, high redshift supernovae should be farther away than you'd expect in a universe with a constant expansion rate, and if they're farther away, they should appear dimmer. Wait, let's pause here. This is the heart of it. This is the crucial, tricky part. In the decelerating universe everyone expected, the distant supernovae should appear dimmer than they would in a universe expanding at a constant rate. This is what both teams were fully expecting to see. They were looking for this extra dimness. They were ready to measure it and calculate the braking power of gravity. But that's not what they saw. When both teams finally finished collecting their data, painstakingly measuring dozens of these distant supernovae, and plotted their points on the graph, the line didn't go the way it was supposed to. The most distant supernovae, the ones that exploded when the universe was half its current age, weren't just a little dim. They were much dimmer, fainter, way, way fainter than anyone had predicted. At first, they didn't believe it. They assumed they'd made a mistake. A huge, embarrassing, idiot mistake, as Brian Schmidt of the High Z team later put it. This is where the streetlight analogy becomes so powerful. Let's walk through it slowly. Imagine you're standing on a long, dark, straight road at night. You see a streetlight in the distance. You have a radar gun, and you clock the car next to that streetlight moving away from you at 60 miles per hour. Based on that speed, and assuming the car has been going a roughly constant speed, you'd expect the streetlight to be, say, 10 miles away. But when you look at the streetlight, it doesn't look like a streetlight 10 miles away. It looks incredibly faint, as dim as a streetlight normally looks when it's 20 miles away. This is confusing. The car's current speed is 60 mph. If it had been doing 60 mph the whole time, it should be 10 miles away and the light should look a certain brightness. But it looks much dimmer, meaning it's actually 20 miles away. How can the car be 20 miles away if it's only going 60 mph now? The only possible explanation is that the car wasn't always going 60 mph. It must have been going slower in the past. It must have accelerated. It must have been puttering along at 30 mph for a long time, covering less distance, and then only recently stomped on the gas to get up to 60 mph. Because it spent so much time going slow, it didn't cover much ground, so it's still relatively close. But then it accelerated, and now it's speeding away. Its current speed is high, but its average speed over the trip was low, so it hasn't traveled as far as you'd think for its current speed. Now translate this back to the supernovae. The supernova's redshift tells us the expansion velocity of the universe. At the time the light was emitted, billions of years ago. Its faintness tells us its distance, which tells us how much the universe has expanded since then. The supernovae were too faint. This means their host galaxies are farther away than we expected for their measured redshift. The only way for the universe to have put those galaxies so far away, to have expanded so much in the time since that light was emitted, is if the expansion was slower in the past than we thought. And if the expansion was slower in the past, that means it must have sped up since then. The expansion of the universe is accelerating. The brakes aren't on. Someone, or something, is pressing the gas pedal. Hard. The data was undeniable. Both teams, working completely independently and actually competing fiercely with each other, were arriving at the same terrifying, universe-shattering conclusion. The universe was not slowing down. It was speeding up. This wasn't just a new fact. It overturned everything. Gravity attracts. How could everything be flying apart faster and faster? What could possibly be stronger than the collective gravitational pull of all the matter in the cosmos? It was like throwing a ball into the air and watching it not only fail to fall back down, but shoot away into the sky faster and faster until it disappeared. It was crazy. Of course they were terrified. This was career-ending stuff if they were wrong. So they became their own most vicious critics. They spent months trying to kill their own result. They looked for any other possible explanation for why those distant supernovae were so faint. Maybe it's dust. Interstellar dust between us and the supernova could dim its light, making it look farther away than it is. But dust dims blue light more than red light. It makes things look redder as well as dimmer. When they analyzed the light, the supernova weren't redder than they should be. They were just dimmer. It wasn't dust. Maybe the supernovae themselves are different? Could the ancient supernovae be intrinsically fainter? Maybe the white dwarfs that exploded long ago were different somehow. But when they analyzed the light curves, the very specific way these explosions brighten and fade, and their spectra, the detailed fingerprint of the elements in the blast, they were identical to nearby ones. The physics was the same. They were perfect standard candles. Maybe there's some other astronomical weirdness. They checked and rechecked every step of their analysis, their calibrations, their equipment. There was no error. The result was real. The universe's expansion was accelerating. There was no way around it. The only conclusion was that empty space itself must contain some form of energy, a kind of anti-gravity that creates a repulsive force, pushing galaxies apart. This energy had to be smooth, not clumpy like matter, and it had to be weak on the scale of galaxies, but dominant on the scale of the entire universe. What could they call it? They reached back into history and pulled out the term that Einstein had invented and then discarded in embarrassment. They called it dark energy. resurrecting the cosmological constant, not as a force to hold the universe static, but as a force to drive it apart. Einstein's biggest blunder turned out to be his most prescient idea. The teams announced their findings in 1998, and the world of physics has never been the same since. The confirmation of this acceleration was the first and most direct line of evidence for dark energy. It earned Saul Perlmutter, Brian Schmidt, and Adam Rees, a key member of Schmidt's team, the 2011 Nobel Prize in Physics. But science requires more than one line of evidence. A single measurement, no matter how precise, can always have hidden systematic errors. To be truly sure of something as monumental as dark energy, we needed other, completely independent ways to probe the history of cosmic expansion. We needed to triangulate the truth, and fortunately for us, the universe in its infinite cleverness left behind a pristine ancient crime scene photo. It's not a photo made of light and shadow, but of microwaves and temperature. It's the cosmic microwave background, or CMB, and it is quite simply the most important fossil in all of cosmology. To understand the CMB, we have to take a journey back in time, all the way back to the very beginning, or almost. We're talking about when the universe was incredibly young, hot, and dense. Imagine all the energy and matter that today makes up hundreds of billions of galaxies, each with hundreds of billions of stars, all compressed into a space smaller than a single atom. It was a searing, chaotic soup. For the first several 100,000 years, the universe was so hot that atoms couldn't even form. Electrons, protons, and neutrons were all zipping around freely, and photons, particles of light, were trapped in the chaos. Why? Because a free electron is a terrible bully for light. A photon trying to travel through this soup would immediately smack into a free electron and get scattered in a random direction. It couldn't travel in a straight line. It was like trying to see through a thick, impenetrable fog. The universe was opaque. You couldn't see through it, not even a little bit. It was a glowing, blinding plasma. But then, a pivotal moment happened. About 380,000 years after the Big Bang, the universe had expanded and cooled just enough. The temperature dropped below a critical threshold, around 3,000 degrees Celsius. Suddenly, the free electrons could be captured by protons. They combined to form the first simple atoms, mostly hydrogen and a little helium. This process is called recombination. Think of it like a sudden cosmic rain, where the free electrons rained down onto the protons to form atoms. And this had a stunning consequence. With the free electrons now locked up in atoms, the photons suddenly had nothing to bump into. The fog lifted instantly. The universe, which had been opaque for its entire existence, became transparent. And those photons, which had been bouncing around for 380,000 years, were suddenly set free. They could now travel in straight lines, unimpeded, across the expanding cosmos. That event, the moment the fog cleared, is called the surface of last scattering. It's the farthest back in time we can possibly see with light. We can't see to the Big Bang because the universe was opaque before that. But we can see this ancient afterglow, the flash of light from the moment the universe became transparent. And here's the mind-blowing part. Those photons are still traveling today. After racing across the universe for 13.8 billion years, they are still here. The expansion of the universe has stretched them out tremendously. Their wavelength, which was once short, like visible light, has been stretched all the way into the microwave part of the spectrum. But they are here, and we can detect them. In 1964, two radio astronomers named Arno Penzias and Robert Wilson at Bell Labs in New Jersey accidentally discovered this radiation. They were using a giant, sensitive horn antenna to study radio waves from space, but they kept finding this persistent, annoying hiss of static that came from every direction in the sky. They thought it might be pigeon droppings in their antenna. They cleaned it out meticulously, but the hiss remained. It was the same no matter where they pointed the antenna. It was the universe itself, whispering to them. They had stumbled upon the CMB, the cooled remnant of the Big Bang's fiery birth. It was the most spectacular accidental discovery in the history of science, and it earned them a Nobel Prize. Now, if the universe were perfectly smooth and uniform at that moment, 380,000 years after the Big Bang, the CMB would be perfectly smooth and uniform in temperature. But it's not. And this is where it gets really interesting. When we map the CMB with incredibly sensitive instruments, like the COBE, WMAP, and later the Planck satellite, we see that it is not a featureless glow. It is covered in tiny, tiny variations in temperature. We're talking about differences of mere millionths of a degree. Some patches are ever so slightly hotter and denser. Others are ever so slightly colder and emptier. These tiny ripples are the single most important thing in the universe. Why? Because they are the seeds of all structure. They are the primordial blueprints. Those slightly denser, hotter patches had a tiny bit more gravity. Over billions of years, that extra gravity pulled in more and more matter from the surrounding areas. They grew. They coalesced. They became vast clouds of gas, which collapsed to form the first stars, which gathered into galaxies, which clustered into the great cosmic web we see today. Every galaxy, every star, every planet, and every one of us originated from one of those tiny, millionth of a degree fluctuations in the ancient CMB. We are literally made of star stuff that came from cosmic ripples. But these ripples are more than just seeds. They are a cosmic fingerprint. By studying their pattern, their size, their distribution, their spacing, cosmologists can extract a staggering amount of information about the universe. It's like the universe did an ultrasound on itself 13.8 billion years ago, and we're just now learning how to read the image. The most important feature in this pattern is the size of the most common ripples. Think of the early universe as a musical instrument. The hot plasma was like a ringing bell. Sound waves, pressure waves, rippled through it. The distance these sound waves could travel in the 380,000 years before the fog lifted is a fixed physical distance. It's a standard ruler imprinted on the sky. We know how long that ruler should be from the physics of the early universe. Now, when we look at the CMB sky, we see these ripples projected onto a giant sphere around us. We measure their angular size, how many degrees they take up on the sky. This angular size depends on the geometry of the universe. Imagine you have a ruler of a known length. If you hold it close to your face, it will look large and take up a lot of your field of view. If you hold it far away, it will look small and take up a tiny angle. Now, imagine the fabric of space itself is curved. If the universe has positive curvature, like a sphere, light rays bend toward each other. This would make a distant object appear larger than it should. Our standard ruler would appear bigger on the sky. If the universe has negative curvature, like a saddle, light rays bend away from each other, making distant objects appear smaller. Our standard ruler would appear smaller on the sky. But if the universe is flat, if its geometry follows the classic rules of Euclid we learned in school, then light rays travel in straight lines. and the angular size of an object tells you its true distance directly. The Planck satellite measured the angular size of those most common ripples with exquisite precision, and the result was clear and definitive. The universe is flat. The ruler appears exactly the size it should for a flat geometry. This is a profound result. In the equations of general relativity, the geometry of the universe is directly tied to its density. A flat universe means that the total density of all the energy and matter in the cosmos is exactly equal to a specific critical density. It's a perfect balance. So Planck gave us a precise number for the universe's total energy budget. But that's only half the story. The pattern of the ripples also tells us what that energy budget is made of. Different components affect the growth of these ripples in different ways. Ordinary matter, protons, neutrons, us, and dark matter clump together under gravity. Their presence enhances the growth of the ripples. By analyzing the detailed statistics of the ripple pattern, Planck could tell us exactly how much of this clumpy stuff there is. The answer: normal matter makes up about 5% of the critical density. Dark matter makes up about 25%. Together, matter of all kinds makes up about 30% of the universe. But wait, we just said the universe is flat, which requires the total density to be 100% of the critical density. We've only accounted for 30%. Where is the other 70%? It has to be something else. Something that doesn't clump. Something that is smooth and uniform, spread evenly throughout the vacuum of space. Because if it clumped like matter, it would have left a different fingerprint on the CMB ripples. The only thing that fits the bill, the only component that can make up that missing 70% and be perfectly smooth, is dark energy. The CMB, a baby picture from 13.8 billion years ago, independently and powerfully confirms the crazy story told by the supernovae. It says that most of the universe is not matter at all, but this mysterious, repulsive energy infused in space itself. The two most powerful probes of cosmology, one looking at the ancient universe and one looking at the relatively recent universe, both point their fingers at the same invisible culprit. The case for dark energy was no longer based on a single, shocking measurement. It was now rock solid. The universe itself, in its oldest light, was testifying to the existence of its own most mysterious component. But wait, there's more. A third, completely independent line of evidence comes from the large-scale structure of the universe itself, the cosmic web of galaxies and clusters. We can map this structure through enormous galaxy surveys, like the Sloan Digital Sky Survey, which has meticulously charted the positions of millions of galaxies. This map isn't random. It shows a vast web of filaments and clusters with huge voids in between. This structure also grew from those tiny ripples in the CMB. Gravity acted over billions of years to pull matter into the denser regions. But the growth of this structure is influenced by the expansion history of the universe. If the expansion is accelerating, as dark energy suggests, it acts as a kind of inhibitor to the growth of structure. Think of it like trying to build a sand castle while the tide is coming in. The rising water, the accelerating expansion, makes it harder for the sand grains, the galaxies, to clump together. By measuring how clustered galaxies are on very large scales, and by seeing how that clustering has evolved over time, astronomers can again probe the expansion history. And once again, the data points to a universe where, about 5 billion years ago, the gravitational pull of matter, which was becoming more and more diluted as the universe expanded, was overcome by the repulsive push of dark energy. The growth of the cosmic web slowed down, the tide started coming in. These three pillars, the supernovae showing acceleration directly, the CMB showing a missing 70% of the universe's energy budget, and the large-scale structure showing suppressed growth, all converge on the same stunning conclusion. Dark energy is real, and it dominates the cosmos. So here we are. We've followed the evidence, and it's led us to a breathtaking and humbling conclusion. We are sure, with a very high degree of confidence, that dark energy exists. It's not just a theory, it's a phenomenon that has been measured, confirmed, and cross-checked. It makes up about 70% of everything in the universe. But this is where the real mystery begins. The detective work has identified the culprit, but we have no idea who this culprit is. We've caught the universe red-handed, accelerating, and we've named the force behind it, but the name is just a placeholder for our ignorance. Dark energy is essentially a fancy term for we have no clue what this is, but it's doing something. So, what is it? This is the million-dollar question, the grand prize at the frontier of modern cosmology, and the answer, if we ever find it, will likely rewrite the textbooks of physics. The simplest explanation, and the one that all our current data fits like a glove, is that dark energy is exactly what Einstein first imagined all those years ago, though for a different reason. It is the cosmological constant. It is an energy that is an intrinsic property of the vacuum of space itself. To understand this, we have to rethink what we mean by nothing. We usually think of a perfect vacuum, of empty space, as being just that, empty, nothing, a void. But quantum physics, the rules that govern the universe on the very smallest scales, tells us that this idea is completely wrong. Empty space is not empty. It is seething with activity. It is alive with a furious, bubbling chaos. At the quantum level, the universe operates on a sort of cosmic credit system. The famous Heisenberg uncertainty principle allows for particles and energy to spontaneously pop into existence out of nothing, borrowing energy from the vacuum, so long as they disappear again almost instantly, paying the energy back. These are called virtual particles. They are particle-antiparticle pairs that flicker in and out of existence in an unimaginably short span of time. This isn't just speculation. We see the effects of this in laboratory experiments. This frantic, endless dance of creation and annihilation is happening everywhere, all the time, in every single cubic centimeter of what we perceive as empty space. This roiling, bubbling, subatomic activity is what physicists poetically call the quantum foam. And all this activity, this foam, should contain energy. This is the concept of vacuum energy. The vacuum isn't a dead state, it's the lowest energy state, but that state is not zero. It should be fizzing with a background energy. This, many physicists believe, could be the source of the cosmological constant. This vacuum energy would have a repulsive gravitational effect. It would push space apart. And because it's a property of space itself, as the universe expands and more space is created, more of this energy comes into existence, leading to a runaway effect that could explain the accelerating expansion. It's an elegant idea. Dark energy isn't a thing out there. It's a property of the nothingness everywhere. There's just one tiny, enormous, universe-shattering problem. It's arguably the most embarrassing, the most profound, and the largest discrepancy in all of science. When physicists try to actually calculate how much energy this quantum foam should have, based on our very well-tested theories of quantum mechanics, they get a number. And this number is so catastrophically, ridiculously wrong that it's laughable. It is wrong by a factor of 10 to power 120. That's a 1 followed by 120 zeros. Let's try to grasp the scale of this error. The number of atoms in the entire observable universe is about 10 to power 80. So this error is a number that is 10 to power 40 times larger than the number of atoms in the universe. It's an error so vast it transcends mere mistake and enters the realm of the absurd. If the quantum vacuum really had this much energy, the repulsive force would be so unimaginably strong that the universe would have been ripped apart in the first fraction of a second of its existence. Atoms could never have formed, let alone stars, galaxies, planets, or people. The universe would be a featureless, accelerating void. The fact that we exist to even ask the question is proof that this calculated value cannot be right. Our universe exists in a state of breathtakingly delicate balance, and this calculation is off by more than a rounding error. It's off by every conceivable measure. It's the worst prediction in the history of physics. This is known as the cosmological constant problem, and it is a screaming clue that something is profoundly missing from our understanding. So, where does this leave us? We are faced with a thrilling crossroads. Either our understanding of the quantum vacuum is completely and utterly wrong in some way we haven't yet grasped, or dark energy is not the cosmological constant. It is something else entirely. This is where the fun really begins, because it forces physicists to dream up other, even more exotic possibilities. One leading idea is that dark energy is not a constant after all. Maybe it's a dynamic, evolving energy field that permeates space. This idea is sometimes called quintessence, named after the fifth element of ancient Greek philosophy, after earth, air, fire, and water, a substance that permeated the heavens. Unlike a cosmological constant, which never changes, a quintessence field could change in strength over time. It could be weak in some epochs and strong in others. Maybe it's diluting away as the universe expands, or maybe it's interacting with matter in subtle ways we haven't detected. This would mean the acceleration of the universe might not be a permanent feature. It could change in the future. This is a compelling idea because it solves the why so small problem. The field could naturally settle into a very low energy state, unlike the quantum vacuum calculation. Another, even more radical possibility is that we've been looking at the problem from the wrong angle entirely. Maybe dark energy isn't an energy at all. Maybe it's a sign that our theory of gravity itself is incomplete. Einstein's general relativity has passed every test we've thrown at it with flying colors for over a century. But all those tests have been within our solar system or in strong gravitational fields, like around neutron stars. We have never been able to test it precisely on the largest possible scale, the scale of the entire cosmos. What if general relativity, as magnificent as it is, starts to break down on these cosmic scales? What if gravity behaves differently when dealing with the vast emptiness between galaxy clusters? Perhaps the acceleration isn't being caused by a mysterious dark energy, but is instead a symptom of gravity itself weakening over immense distances in a way that Einstein's equations didn't predict. Modifying general relativity is a daunting task. It's a masterpiece of such elegance that tinkering with it is like trying to improve a Mozart symphony, but the mystery of dark energy forces us to consider it. So, how do we solve this puzzle? We don't do it with pure thought alone. We go back to the cosmos and we measure. We measure with more precision than ever before. This is the goal of a new generation of astronomical projects. Instruments like the Dark Energy Spectroscopic Instrument, DESI, which is not a traditional telescope, but an ultra-sensitive robotic eye that can capture the light from thousands of galaxies simultaneously, building a gigantic 3D map of the universe. Or the Euclid Space Telescope, a European mission specifically designed to be a dark energy detective, mapping the shape, distribution, and movement of billions of galaxies across time and space. What are they looking for? A tiny, telltale sign in the data. They are trying to measure with exquisite precision exactly how the expansion rate has changed over the history of the universe. If dark energy is truly Einstein's cosmological constant, then its strength has been unchanging and the acceleration has been steady. If, however, the data shows that the acceleration has been changing, speeding up or slowing down over billions of years, that would be the smoking gun for something like quintessence, a dynamic field. They are also looking with extreme precision at the growth of the cosmic web, the clusters and filaments of galaxies. A cosmological constant and a modified gravity theory might affect the clumping of matter in subtly different ways. These incredibly sensitive measurements are our best hope for distinguishing between these wildly different ideas. The quest to understand dark energy is more than just an academic exercise. It is a fundamental inquiry into the nature of reality. It asks, what is space? Is it just a passive stage, or is it an active player with its own energy? What is the fate of our universe? Will the acceleration continue forever, eventually tearing apart all structures, even atoms, in a big rip? Or will it change? And ultimately, are our laws of physics, which work so perfectly in our local neighborhood, truly universal? The mystery of dark energy is a gateway to a deeper understanding of everything. It's a reminder that the universe is far stranger, more wondrous, and more mysterious than we ever thought, and that the greatest discoveries often lie not in the answers we find, but in the new and more profound questions they force us to ask. So, how are we sure dark energy exists? We are sure because multiple independent detectives, using different tools and looking at different clues, have all been led to the same suspect. The supernova hunters caught the universe in the act of accelerating. The CMB cosmologists took a baby picture of the cosmos and found that 70% of its energy was missing from the matter budget, a void that only dark energy could fill. The galaxy mappers saw the lingering effects of this energy suppressing the growth of the cosmic web. The evidence is overwhelming and consistent. It tells us a humbling story. The universe we thought we knew, one dominated by the familiar pull of gravity and the stuff of planets and stars, is just a minor component. The cosmos is primarily made of two profound mysteries: dark matter, which pulls, and dark energy, which pushes. We are adrift on a dark ocean, and we have just begun to sense the strange currents that flow through it. We have measured their effects with stunning precision, even as their ultimate nature remains hidden from us. It is a reminder that the universe is far stranger, far more wondrous, and far more mysterious than we ever imagined. And the search to understand this mystery, to grasp the nature of this dark energy that shapes our cosmic destiny, is one of the greatest adventures of the human spirit. It is a journey into the dark, guided by the faint light of distant explosions and the faint whisper of the Big Bang's echo. And it is a journey that is only just beginning. Good night, and have a deep sleep.